So, oh yeah, audio works, perfect. Thank you for the nice intro, and well, of course, thank you to everyone who's involved in organizing this conference. I mean, Marco put up a team of, I don't know, 70 people, and I know, because I've done that myself, that this isn't like a really tough job, and they've done it so well. So thank you very much for inviting me, and thank you to everyone who's involved in keeping this event up and running. Yeah, so that's kind of me. Well, throughout the internet, people know me as ASCII-Disco, like on Twitter and GitHub, etc. I do work for a company maybe some of you heard of, Deutsche Telekom, but I'm not like, so I started out as a front-end engineer there, and I've been working in the world of consumer IoT, but we're not going to talk about IoT today, at least not that much. If you have any questions and don't feel comfortable asking them here or approaching me later after the talk, you can always shoot me your questions on Twitter, and if you don't use Twitter, you can use my email address, public@ascidisco.com. So, does anyone know what that is? Yeah, thank you. It is the Berlin Wall, and it is probably the most iconic symbol for the separation of East and West Germany back in the day. So, I mean, before the German reunification in 1990, Germany's capital wasn't Berlin. It was like the tiny city of Bonn, which was kind of like here. And aside from that, like not only Bonn was the capital, but all the agencies, the government agencies and the councils, they were kind of like spread all across Germany. So you had some in Hamburg, you had some in Munich. But, you know, 10 years after the reunification of Germany, Berlin became the capital. And later on, the government moved over from Bonn, and then other parts of the government followed, and then companies followed, and that caused problems for many smaller towns who hosted those government agencies and councils. They not only needed to cope with like the loss of jobs, but also, even worse, well, young people leaving the cities, everyone's moving to Berlin, and Germany, which was this wonderful decentralized country, kind of like became centralized, like every other European country, like Paris in France or London in England. But yeah, I mean, all of this reminded me of something as a developer, as someone who works with the internet. If we take a look at how the internet works today, we basically see the same thing. We see a few central services that we're bound to use every day, and many users have moved on from tiny, independent, self-hosted things to, I don't know, if they want to do video conferencing, they use Skype and stuff like that. If you have IoT devices, you have a Nest or NetAtmo, which is like Nest belongs to Google, and everything is going through their servers. Code as developers, you know, we use GitHub to store our code. We use Bitbucket or whatever, so central entities. Messengers, it's the same thing, WhatsApp, Facebook. Files, Dropbox, even worse. So there's not really a competitor to Dropbox that really has caught on. And yeah, so what we did is we built ourselves a wonderful centralized internet. And I mean, that a workflow, if one of those services just bails out for some reason, then, well, a whole workflow is ruined, or day is ruined. And I don't know, we just rely on all of those services, the central points of failure. And to me, this kind of sounds hilarious. So I think we should start thinking about other ways to distribute data to. Maybe we should think about getting rid of those central access points, those central points of failure, as I'd like to call them, and instead organize like our everyday lives and our workflows around tiny building blocks, tiny components that do one thing well and then communicate with each other directly. I mean, I think that would be wonderful for some ways. I mean, it could not only help us to circumvent outages, it would enable us to, well, save our privacy, at least a bit more, make surveillance nearly impossible, at least very hard, get rid of censorship because there is no central entity who could censor things, and also, I mean, of course, help us to prevent massive privacy breaches and data leaks, because if the data is distributed into many like tiny nodes who only hold a portion of the data, well, there is no way to get, well, of course there are always ways, but usually it's very hard to have like this massive privacy breach or leak, because people could only extract a fraction of the data. So what we really want is to have a decentralized internet. We really want to have peer-to-peer interaction, where we directly communicate with others without the need for a server at all. And today I'd like to, well, dive into one of the major technologies that can make this future happen. And to me, this is WebRTC. So usually, you know, WebRTC from applications like Google Hangouts or Appearin and stuff like that. But WebRTC isn't only there for audio or video calls. It's capable of so much more than just audio or video. Maybe even it's capable of being the great liberator of the internet, but well, I won't go that far. And yeah, when we start thinking about how WebRTC works, we should start with a technology many of us should be familiar with, which is WebSockets. So with WebSockets, a communication between two systems or like two browsers looks like this. We have a central entity in the middle, the server, and every message that we want to send to the other browser needs to pass through this server. So this server is, well, the man in the middle that needs to broker our messages to everyone. With WebRTC, that looks a bit different. So there is no server, it just isn't. What we have is two clients that can directly talk to each other, that can exchange messages. If we express this in JavaScript code, it's, I would say, not that much. It's quite okay and readable, because all you need is to, well, set up a peer connection with the other peer that you want to get in touch with. Then you have to create a so-called data channel, which is basically the same thing as you would do with opening a connection with WebSockets. And yeah, after that, all you need is to register some message handlers that are called when a message is received, and yeah, implement a way to send data somewhat. This is basically all you need for the communication between two peers. What is a bit more tricky is how those peers are gonna find each other and how they are gonna communicate, so the initial setup of the communication. We're gonna talk about this a bit later. So first of all, let's talk about the data flow and the data model. So the protocol used to transfer data if you use WebRTC is called SCTP. That stands for Stream Control Transmission Protocol. By the way, in WebRTC land, the WebRTC people use a lot of acronyms and abbreviations. We're gonna see a few of them today, no matter what. Just, you don't need to remember them really. You just need to be able to Google them if you see like the abbreviation, I would say. So SCTP as a protocol is really interesting, as it can work in two different modes. In an unreliable mode, which is basically analog to UDP, and in a reliable and ordered mode, which is basically analog to TCP. So reliable and ordered mode, they guarantee the transmission of messages and also the order in which they are, well, received by the other end. And the thing is, yes, this takes extra overhead. So this mode is potentially slower than using a UDP-like transmission where data is unreliable and unordered. So if you have a video stream or a video conference where it's okay if, well, some of the bits get lost on the way, then you probably would use UDP. Then you probably would SCTP analog to UDP in the unordered mode because it's just faster. You're able to shovel more data in a shorter amount of time through the wire. But if you want to transfer data, then you probably would use the reliable and ordered mode, which is kind of like analog to the TCP world we know. Not 100% syntactically correct, but I think that shows how simple WebRTC can be configured to just behave like TCP or just behave like UDP. And now on to, well, let's say the hardest bit, or the thing that people find really or struggle with the most when they get started with WebRTC, which is the signaling and discovery. So as said, before we are able to use this simple way to exchange data between the peers, we need to find a way to, well, find our peers. And in order to know how to find, well, each other, we first, as a client, need to know who we are and where we are. So we need to know our own IP in a local network, but also in the wide area network, because usually the peer we're going to, well, start a data exchange with, or want to start a data exchange with, is not in our local network. It can be, well, on the other side of the world. So we need to know our public IP as well, and we need to know how to tell others where they can find us. So this is where the so-called stun server comes into play. It can tell us who and where we are, basically. So stun stands for Session Traversal Utilities for NAT, and NAT stands for Network Address Translation. So basically the whole thing would read out as Session Traversal Utilities for Network Address Translation, which is just ridiculous. But yeah, so if you boil it down to the most basic thing, you could say, okay, the stun server tells us our local IP address in the wide area network, and it also then tells us if we can use WebRTC, if we can bypass the firewalls that maybe our router has set up and everything. So it basically lays out the path for the communication that is going to happen later. By the way, you don't need to roll your own stun server. There are many, many public stun servers, for example, by Google or by basically every telecommunications company out there that you can freely use for this kind of like setup for your data transfer. Then we need a way to announce this data, so the thing that we just figured out, who we are, where we are, our IP address, etc. We need something in the middle. We call this turn server, not turn server, we call this turn, and that is basically helping us to find other peers, so people or clients or other applications we want to have contact with, and then and also helps us to transmit the data to them. So turn, again, stands for traversal using relays around NAT, and turn is effectively a proxy that can also act as a fallback server. So the turn server can not only help us with finding peers, it also can act as a fallback mechanism, because in 20% of the cases, at least this is what my personal research has shown, WebRTC connections are not being able to establish because people have set up very rigid firewalls, etc. So then you need basically a fallback, which is a turn server that also acts as a WebSocket server, for example, to again use a central point to transfer the messages, but that should happen transparently in the background. And yeah, you might have seen also ICE on that diagram, written a couple of slides ago. And basically, ICE stands for Interactive Connectivity Establishment. And ICE is basically not a single technology. ICE is like the umbrella framework for all those technologies like stun and turn, etc., that is there to connect us with our peers. I mean, there are quite many reasons that a straight-up connection from peer A to peer B simply won't work. As said, like there might be a firewall in the way or anything, something in that direction. And the thing is, you know, thanks to the limitations of IPv4, we're not able to give every of our internet-connected devices a public address, because thanks to the way IPv4 addresses have been designed, they are limited to 4.2 billion different combinations. So we have a max at 4.2 billion IP addresses in the public scope, which, well, we've exceeded that by far since a long time. We have more than 4.2 billion devices connected to the internet. So what we need to have is basically a restriction that all of our devices in a local network just have a local address. Then we have a router which gets a public address, but usually you don't have a static public IP address. You usually have an address which changes over time and is shared with others as well. So, I mean, yes, there are ways like IPv6 maybe will help, well, of course will help with this because we have a much broader address scope, and basically, yeah, every device on this planet can get its own IPv6 address. But with IPv4, which is still the standard, and to be honest, I think will be the standard for quite some time, we have to find a ways around that. And yeah, this is what basically ICE in the WebRTC scope is for. It helps us to circumvent all those problems that we face because of the limitations of IPv4. But yeah, the cool thing about WebRTC is it's not tied to one specific signaling mechanism. It's very flexible. So for example, you don't need a turned server, as signaling can happen out of band. And with out of band, I mean, you could write someone a letter and send it via snail mail or a postcard with your connection details, and they could type it into their application. I mean, you could even send a carrier pigeon with like the information hanging around its neck, and then people could just type that in and have a straight up connection to you right away. So in the next examples, we're gonna use a server that it's called the dealer, which comes from basically the poker game. That's basically the person who hands out all the cards. So we're gonna use this server, which is a total proprietary implementation, to figure out a way to connect the peers and start a data exchange. So it all starts with the so-called offer. So if one of the peers wants to initiate the communication, it needs to generate an offer and transfer it to the signaling server. So basically say hi to the signaling server, hi, I'm here. And for that, it needs to send a message which is encoded in the so-called session description protocol. Doesn't matter what's in there, but basically this SDP message contains all the data that's needed for other peers to connect and for the signaling server to figure out where that specific peer is that sent this message. Signaling itself, as said, WebRTC is quite flexible. There is no standard. You can even use carrier pigeons to send out the data. So signaling is not built into the WebRTC stack in a browser. So you have to kind of like roll your own. That's the thing. But before we even send out the offer, we need to create it. So this is basically containing the metadata you've just seen on the last slide. So we create the offer. We apply this offer to ourselves. So we basically sign ourselves with that offer so that if basically the other peer later on returns with an answer, we can be sure that this was basically an answer to the offer we send. Yeah, we just need to dispatch this somehow to the server. That's up to you. And then the signaling server, if there is another peer, we call it a recipient in this picture here. If there's another peer that says hi to the signaling server, they can get our local description, our offer that we generated, as the so-called remote description on their end by the signaling server. Then they apply it and create an answer to that, which they again dispatch back to the signaling server. So in code, it's basically like an event handler. If the signaling server says, well, you know, there is an offer from another peer, you basically set that as your remote description in the local client, and then you, well, create an answer based on this offer that you got from the other peer. Set that as your own local description, so basically sign off yourself and send that back to the signaling server. Last step then, okay, so the initiator has sent its offer, we set our remote description and created an answer, so the signaling server then needs to dispatch our answer then as the remote description to the initiator back, which the initiator then needs to set as its remote description for this data channel, for this data communication channel. So after that, like, we're basically done. So both peers gonna do a handshake in the background, exchange some encryption keys, etc., and then are ready to talk to each other. So we have a stable connection between two browsers here. Everything else is now out of the game. Those two are there talking with each other, and there is no server involved anymore. Another great thing, so as I said, as I mentioned in the beginning, I do work in the field of IoT. So I do work with a lot of devices in people's homes, as I work in the field of, well, consumer IoT, also known as smart home. And one of the biggest challenges that we face, one of the biggest problems is what to do with the user's data. Because we actually, as a company who has quite high standards when it comes down to privacy and, well, the anonymous user. So we don't want to know that much about our users. We don't want to know if there's like 25 degrees in their living room right now. And so we thought, okay, maybe WebRTC might be great, because for us, it would eliminate large parts of a server infrastructure that are just used to relay messages maybe between consumers' local mobile clients and their local devices, because all the local devices needed to dispatch their information. It was going through our servers or server infrastructure, because it was received by one end, was then somehow computed, encrypted, and sent back to the user's mobile app, for example. And yeah, so we thought maybe we could make this life quite easier for us, and also then prevent things from happening, like somebody stealing data from the servers, from our servers, because there are no servers anymore, no data. Because, well, we could just use WebRTC on our devices in the people's homes themselves. And the good thing about WebRTC is it's not just meant for the browser, it's available everywhere. So if you're building React Native applications, well, there's a plugin that works. If you build native applications in Android or iOS themselves, works. If you build things based on, I don't know, C++ or whatever can have C++ bindings, like Node, for example, there is a WebRTC library that you can use. So basically, WebRTC is available everywhere. So everything else in the picture we saw will stay the same. We've only exchanged one of the browsers, so one of the peers, with, let's say, a Raspberry Pi that is just there as a prototype device and dispatching data. Effectively, well, we kind of like use our device or Raspberry Pi like a server in this scenario. You know, in WebRTC there is no server and client because everyone is a peer, but we kind of like used the Raspberry Pi as a server there. We only had then like one problem because we had a stack that was already working. We had a REST interface, we had a server infrastructure running on Express, and yeah, we were using Vue. And the thing is, none of those frameworks, none of those well-designed things that you just want to use, those battle-tested frameworks that you usually use in your front-end applications or even on the back-end, can talk WebRTC. You could say, yeah, I mean, you know, Vue is just, or React, this is just a view layer. It doesn't matter how the data flows in. But, I mean, the ecosystem is basically modeled around exchanging data either via HTTP or via WebSockets. WebRTC simply isn't in a game. And the problem is, so we had to make a decision then. So what do we do? Do we throw away all those battle-tested frameworks and start rolling around just because we want to use WebRTC, and all of that isn't really well supported? But yeah, I mean, that would be quite impractical because we would definitely need to roll out a lot of code on our own and won't be able to use their technologies. So we ask ourselves, is there maybe a way to like have the cake and eat it too? And especially for mobile, the answer was easy to find because basically everything could be intercepted. So we were like, yeah, fine. But for the web, it was a bit harder. But in the end, we settled on using a service worker to communicate as a man in the middle. If you don't know about service workers, let's have a quick look at them. So basically, a service worker is a tiny JavaScript file that runs outside of your main process in your browser. And basically, all HTTP requests on a particular domain, the domain the service worker is also registered on, can be, well, basically flow through the service worker. So what we thought, okay, if we have each and every HTTP request, and we can intercept them, and we have a man in the middle, so basically, yeah, why don't we just use a service worker to catch all of the HTTP requests, convert them into WebRTC, send the data via WebRTC to the other peer, and when we receive an answer, convert this back to HTTP. So basically what we wanted to do was emulate HTTP over WebRTC so that we can continue using all the shiny frameworks that we use. Problem there was then that within a service worker, you don't have access to WebRTC. That is just like none of the features that is exposed to a service worker. But we figured out, you know, service workers can pass data to the main thread of the application, and the main thread of the application has access to WebRTC. So we had to write a bit of glue code to make this possible. And in the end, it looks like this. So whenever the browser requests something via HTTP, and this can be anything. This can be just a simple image tag in HTML in the web page, because that generates an HTTP request. So when the browser generates an HTTP request, the service worker catches, intercepts this request. It turns this into some kind of like proprietary format and sends it back as a post message to the main thread of the browser. Looks a bit counterintuitive, but is necessary because only the main thread has access to WebRTC. So the main thread then sends the WebRTC encoded HTTP response back to the other party, back to the other peer, and that answers it with an WebRTC message on their own, which, well, ends up in the main thread of the browser, but we're gonna need this in the service worker, so the main thread needs to post message the content back to the service worker, and the service worker then generates an HTTP response out of this. Astonishingly, this works quite reliable, even though if I I'm not sure if we would really like to use this in a browser in production, to be honest. But, well, at the moment it works. We're still in the prototyping phase. So I have a quick demo here, which is basically just, displays and sync. Oh, good. So I basically have a Node Express server running, but that Express server isn't serving stuff via HTTP. It is basically serving stuff via WebRTC. And I've also have just a simple static web server running. So this is the web page that I'm running. I can refresh it, and it's Mario who wants to, well, get some cat pics from Kirby. And when we open here, then the developer panel here and go to the network tab, we see, well, first of all, the service worker, and secondly, that all of the requests that we do are intercepted by the service worker, so I can reload, always happening the same. So the service worker always answers the thing, but it doesn't answer it from cache like service workers, well, are designed to do. What happens in the background is, maybe I can show you at the node server here. So, because every time just give me a sec, left half, right half. So every time I reload, well, wrong server, the Express server answers this, and we get the data from the remote server here. And so it's not cached. It's coming directly via WebRTC. And usually, like, I don't know, you're used to, well, where we have it here. You're used to, I don't know, Node.js server code that looks like this. So you require Express, maybe require HTTP, and just serve a public folder, right? We wanted to not only replicate this like seamless HTTP communication on the client, but also on the server side of things, and make it compatible with basically every HTTP node framework out there. So let me quickly go back to the presentation. So first, let's take a look at what the service worker does. So it's a bit like reduced this code, but basically if you register a fetch handler, every HTTP request will be converted into an event for the fetch handler. Then we can use a function that requests that resource via WebRTC, do the full hustle of getting back to the main thread, and that sends the WebRTC message and then receives the answer. And, well, if we receive an answer, we can respond with it. If not, we send a 404. As this can be quite weird to deal with at times, we basically made a library out of this. We call it the litterbox library, because all you need to do then is load a signaling script of some kind, load a client in your browser that, well, registers a service worker and does all the magic for you. And then you only need to say, well, everything that I request that is a sibling of this path, of the path RTC, for example, will get fetched via WebRTC. You configure your stun server, you configure a signaling server, and, well, maybe we can even get rid of that, especially in local environments. So if you're on the same network as your peers, we can abuse things like the remote and presentation API or the remote playback API to figure out other peers in a network, which is like an interesting thing to do. Then we set a namespace, so telling the signaling server in that way with which kind of peer or server we want to communicate. And on the server side, it's nearly the same as, well, spinning up a simple Express server, because in the end, you can use any library, if it's Koa, if it's Hapi, or if it's Express, doesn't matter, because we're kind of like mocking HTTP on the node level itself. So every WebRTC message that gets received will be converted into an HTTP response for a node itself. So before it reaches userland code and before it reaches this any server implementation like Express, a node, it is converted into a simple HTTP request message. All you need to do is resemble the configuration that you have in a client that was part of the arguments of the script tag, so that the client and the server find each other, as we, well, discussed. Just to make it easy, they have the same namespace, they know there's done in signaling servers, so they will find each other. And then, instead of, well, adding a port to listen to on a server, we just add our signaling data, and then we have a server that is reacting to WebRTC requests, but internally converting them to HTTP as well. So we can use all the wonderful things like GraphQL Apollo server or whatever, because, well, internally node things as just HTTP. And eventually then, if we have enough always-on devices in people's homes, we could even replace nearly every server component, like stun turn server, the dealer server that we have. We could replace that, because each and every device in your home and in other people's homes could have a small routing table with information about other peers that are maybe not even in their household. So that after the first time, after the first connect, all the clients know which kind of like peers in those great network they can ask, so cache the data in the beginning, and can ask for routing tables to other devices, which is a bit tricky, but in theory, this is possible. And well, I must say the first few times we've played with this, it was extremely hard because latency was quite high, because like every device only knew a fraction of other devices, and if you requested a device which was like really like at the end of the chain, you had to do a lot of hops and a lot of requests, and that increased the latency extremely. But yeah, we're still working on that, and if that succeeds, then we don't have any data in the cloud anymore. We don't need any server anymore except for the initial first-time registration. We just have a fleet of decentralized single devices that can all communicate with each other. Well, to recap the past 30 minutes. WebRTC. It's not only about video conferencing. It's not only meant for the web. There are bindings basically for every programming language, for every technology out there. It is a general purpose data transfer. Data channels allow us to send message, to pass a message between all the peers. We have a bidirectional transfer of text and binary data. Data can be sent in real time. The protocol which WebRTC is based on can be both, can be TCP-like, can be UDP-like, so it's quite universal. And in general, I think it's just like this wonderful-ish new tool in our chain that we can play around with and have fun with. As for the library that I was mentioning, we haven't released it yet, so we've been tinkering with this for, I would say, 6 to 9 months, and we still have a few problems. So what I said, what we wanted still to integrate is local peer connection without stun and signaling servers using the remote playback or presentation API. Firefox sometimes is a bit stubborn, so there are some implementation details in Firefox's WebRTC implementation that do make a few problems and need us to write a lot of code, especially for Firefox. So yeah, we try to cut that code down that we just have to write for Firefox. Well, performance and reliability. This is, I mean, just an experiment, but still we wanted to work it. The library size at the moment is, I think, gzipped 1.5 kilobyte on the client, and we wanted to keep it that way so that there is nearly no additional ballast you get into your client app. Want to create more signaling adapters, maybe even create also WebSocket facade, because this is, well, WebRTC can do this. This is what it was initially meant for, like exchanging just messages in a bidirectional way, which also WebSockets are meant for. But yeah, we haven't written that WebSocket facade yet. Well, in the end, we really need to release the packages because, yeah, at the moment they aren't public. This is all just a big experiment that we're running with a couple of 100,000 devices that are out there in users' homes, which is, well, really interesting, and we are still like in a phase of experimentation. But I do think it's exciting because with this technology, we can really make it happen to have a decentralized way of things that communicate. Doesn't necessarily need to be just web pages, because we are working with IoT devices, and for that, it seems it was meant to do this. No more privacy problems, no issues, no more server components that we need to scale, because everything that happens just in the user land of the actual end customer, from his or her mobile phone to the device themselves. I find this very interesting, and I hope we can somewhat in the future figure something out that just works and that everyone can use, and everyone can just simply convert their HTTP-based communication to WebRTC and get full peer-to-peer protocol. And with that, yeah, thank you very much. And I'm happy to hear questions.
Thank you. So, question number 1. Is there some free turn server? Otherwise, it isn't serverless for us. Exclamation mark.
As far as I know, there isn't a free turn server that you can use if you rely on the fallback of WebSockets. So, yeah, you have to roll that on your own, and there are cases where it doesn't work because of firewall restrictions, etc. That is just the reality. But the thing is, I think you need to think about it like the other way around. If you wouldn't use WebRTC to communicate between the clients, you would have 100% of like all the data flowing through your servers, which, well, traffic costs money, right? And if you use WebRTC and only like 20% of the traffic end up on your server, which we just learned before, you can easily host somewhere else, like on AWS or Azure, then only 20% maybe of the data flow through your server, and that will, well, save you quite a lot of money, especially if you deal with a lot of data coming from video streams, for example, which is just costly and creates a lot of traffic.
Okay, thank you. We have time for only one more question, but I do invite you to approach Sebastian because the questions are really great, on point and technical. So the next question is, could you please tell us again what is the problem using WebRTC in Vue.js and React directly? It is just JavaScript that can be wrapped in a component, isn't it?
Yeah, sure. You can use WebRTC with any framework you like, but we had the problem that we wanted to use more of the ecosystem and the infrastructure. In our example, it was especially GraphQL that we wanted to use. And everything, like all the GraphQL is basically built around HTTP or WebSocket as a transport layer. All the client libraries for Vue or React or whatever, are built around using HTTP or WebSockets for the communication. So what we could have done was like rewrite or write our own GraphQL server component, write our own GraphQL client component that just sends the data via WebRTC, or figure out, as we did, a different way to use the battle-tested client and server technologies that are out there that cannot communicate via WebRTC and just make them communicate via WebRTC. So yeah, I mean, it's just a browser built-in technology. You can use it, of course, with every JavaScript, client JavaScript framework that you like. But we wanted to use all of the ecosystem that is out there, which typically is based on HTTP or WebSocket connection, or WebSocket using it as a protocol or transport layer. And yeah, that was then the reason why we said, okay, let's try to figure out some kind of clever way to, as said, have the cake and eat it too, use the libraries that are out there in the ecosystem without the need to roll around, because we wouldn't be able to do that.
Okay, thank you. So, like I said, please do approach Sebastian and ask your technical questions. And that will be all for now. Thank you, Sebastian.
Thank
Let's
you
hear
very
it
much.
for him.